In this example problem we have a second baseman tosses the ball to the first baseman, who catches it at the same level from which it is thrown. The throw is made with an initial speed of 17.0 meters per second at an angle of 35 degrees above the horizontal. So part A asks, what is the horizontal component of the ball's velocity just before it is caught? So this is very similar to the zero launch angle problems that we covered previously. The only difference is that the initial speed is at some angle. So it just adds one more degree of complexity to the problem, because now the initial speed or initial velocity, when you add the direction to it, we have to break it into its x and y components as well. But as far as like solving the problem, it's still essentially the same as the previous problems that you've seen. So let's start by drawing our second baseman. And for clarity, I'm going to go ahead and draw the first baseman as well. Okay, now that we have our two people drawn, we're going to start drawing or writing down all the information that we're given in the problem. So we know that the second baseman tosses the baseball with an initial speed of 17.0 meters per second at an angle of 35 degrees above the horizontal. So you can imagine that there's a horizontal line drawn through the ball. Okay, there's my horizontal line. And now I just want to go ahead and draw the trajectory of the ball on this picture. So we know that the ball is going to make a parabolic shape. Okay, so it's going to look like a upside down parabola. So it's going to follow this path, okay, generally. And then the first baseman is going to catch the ball. Okay, now let's draw all the information, or write down all the information that we know. We know that the throw is made with an initial speed of 17.0 meters per second at an angle of 35 degrees above the horizontal. So I'm just going to draw the initial speed. Now I'm going to draw this a little bigger than I really have to, just to make it a little easier to see. So my initial velocity is V naught, so V naught equals 17.0 meters per second. Okay, now I'm going to draw my angle, which is 35 degrees above the horizontal. So I write my angle as 35.0 degrees, okay, from the horizontal. Now I can set up my right triangle, because I'm just sort of forward thinking here that we're going to have to break this speed into its x and y components, because that's really the only difference between this problem and the previous problems that we've been working with zero launch angles. So it's pretty clear that if I just draw a line straight down from the tip of my vector to the horizontal line, I will get the right triangle that I need. Okay, draw my little box. And I know that this side of my triangle is straight up and down, so this is going to be my y component, okay, because it's straight up and down like my y-axis. And I know that this side of my triangle is going to be my x component of the initial velocity, because it's perfectly horizontal like my x-axis, so v naught x. Now, another piece of information that we know about this problem, even though it's not explicitly stated, we do know that as soon as this ball leaves the second baseman's hand, that the only force acting on the ball is the force of gravity, okay, which always points straight down. So as soon as that ball leaves the second baseman's hand, your force of gravity is straight down, okay, so that means your acceleration will be equal to negative 9.81 meters per second squared. And because it's perfectly straight down, you know that this is going to be equal to the y component only, so AY. So we can go ahead and make a note too that AX is equal to 0, which will be essential to solving this problem. Now, we're not given any information about the distance between the first baseman and the second baseman, so I'll just label that as XF. We don't know what that is. We may not even need it for this case. All right. Now, the last thing that I really want to label on this picture is the origin. So you guys know that I like to put the origin where the object starts. So we'll say that where the ball starts is the origin, which means that at that point, we know that x naught is equal to 0 and y naught is equal to 0. So at this point, you should really start thinking conceptually about the problem. We know that for part A, we're looking for the horizontal component of the ball's velocity just before it is caught. So you can imagine that this ball follows this trajectory, and when it gets over here, the velocity, the final velocity, will be pointing toward the fourth quadrant, so that'd be like my VF. Okay, and you know that that VF is also going to have an x component. Okay, so it's going to have an x component that's perfectly horizontal. Okay, so the VF x. Now, the fact that the acceleration is 0 in the x direction is essential, because what that means is that our x component of our velocity will not change. It'll be the same at all points as the ball travels to the first baseman. Okay, so whatever this initial velocity x is, it's going to be the same as the final x, because our acceleration in the x direction is 0. So VFX is equal to V naught x. So to solve this problem, all we have to do is just find the x component of the initial velocity. So I'm just going to redraw this triangle on the next slide to make it a little bit clearer what I'm solving for. So let's go there and take a look. So I've already redrawn my right triangle, and I'll put the little 90-degree angle box. And at this point, hopefully you guys are comfortable using trig functions. So we've got SOHCAHTOA, which is just sine is equal to opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay, so let's figure out which sine function we need to use. So in this problem, we know the hypotenuse of our right triangle, so I'm just going to make an educated guess that we need to use the sine or the cosine function. Now we're looking for the horizontal component, so in this case, that would be the adjacent side of the angle that we're given. So V naught x is the adjacent, we know the hypotenuse, so we want to use the cosine function. So cosine of the angle that we're given, so 35.0 degrees, 35.0 degrees is equal to the adjacent side, so V naught x, there's V naught x divided by the hypotenuse, which is 17.0 meters per second. So 17.0 meters per second. So to solve for the x component of the initial velocity, I just multiply both sides by 17 meters per second. So times 17.0 meters per second. Okay, then multiply the other side by 17.0 meters per second. Okay, put that in parentheses. Now on the right hand side, I've got 17.0 over 17.0, so those cancel out, as do my units. So all that's left on the right hand side is just V naught x. And on the left-hand side, I have 17.0 meters per second times cosine of 35 degrees. Okay, so typing this into our calculator, we get approximately